Welcome back to Algebra 1, everybody. Hope you guys had a great weekend. Today we are continuing with Chapter 7, doing 713 more applications of exponential growth. So a couple announcements before we get started. We had homework collection 11 due last week, so please make sure you get that turned in if you have not. We had a quiz last week. We got a quiz this week coming up. We have another homework collection, so make sure you're keeping up on your stuff because we were running out of time this school year. Only about 6 weeks to go or something along those lines. 6 or 7 weeks to go. After today, we're about halfway through Chapter 7, so make sure again you're keeping up with your stuff because we are only about a week and a half out from our Chapter 7 test. So if things aren't making sense, if you're still kind of struggling to get caught up and keep up with stuff, this is a great time to, again, kind of buckle down, get yourself caught back up, ask questions of your grading teacher, because, again, we are running short on time as we finish out this school year. So today, game plan is 713. I'm going to flash the answers up for the homework real quick from over the weekend, and then we will get going from there. So press pause if you want to take a look at these answers in a little more detail. I'll scroll down if you want to check them out a little bit more. Otherwise, perfect. There we go. So 713, how does it grow? More applications of exponential growth. You may have heard the expression in the past, money does not grow on trees. However, money does, in a sense, grow in a savings account. So today we are going to apply our understanding of exponential functions to solve problems involving money and interest. So as we work today, use the following questions to help our thinking. How does it start? How does it grow? What's the multiplier? How is the rate written as a percent and as a decimal? It's a lot of good stuff here as we get started. So let's turn the page, 713, we're going right down to 730. So we're saving for college here in 730. Suppose we have $1,000 to invest and we have two investment options. First, we can invest in bonds, which pays 8% simple interest. We'll talk about that more in just a second. Or put your money in a credit union account, which pays 8% compound interest. So again, there's a big difference between those two. We'll talk about that more in just a minute. Which option is going to make us more money? Which option you choose will the option you choose make a difference in the amount of money you earn? Examine the two situations below. It's early for me too, everybody. All right, so bonds with simple interest. If you invest in bonds with your $1,000, would grow as shown in the table to the right. So how does the money grow with simple interest? So again, our growth is 8% with simple interest. It's also 8% with compound interest, but we'll get to that in just a second. So when we have simple interest, let's see if we can figure out what's happening in our table as we go from our initial value and then up through our table here. So as we go, our initial value is 1,000. After 1 year, our money goes up by $80. So we increase by $80. If we go from year 1 to year 2, we have the exact same increase of $80. And then the same thing again as we go from year 2 to year 3, we're just adding $80 yet again. So the simple interest part is telling us that we are taking 8% of our initial value, and that's what we're adding every single year. So we're adding 8% of the original amount of our initial value. So again, we're taking that 8% of the initial value because 8% of $1,000 is $80. Again, that's what we are adding to every single year as we go forward. So again, very simple growth. We're just adding $80 every single time. So if we want to figure out the balance of our savings account after 4 years, we're basically just going to the next row down in our table. We just got to follow our pattern again, add $80 to the previous one. So we get $1,320. There we go, pretty straightforward. So now let's go down to the bottom part of the page and take a look at part C. Our accounts with compound interest. Instead of investing in simple interest in a bond, now we're going to put it into a credit union saving account. And what that means is we're going to invest with 8% compound interest that is compounded once per year. So again, 8% compound interest. So that simple interest, we're adding the same amount of interest every single year. Compounding is going to be just a little bit different. All right, so its value would grow, like we can see the table right here. Why is the value here? Why is there $1,166.40 in our account at the second year? So if we look at our first table with our savings bond, this number in year 2 was $1,160. So obviously that's not the same. So we're going up by a bigger margin between year 1 and year 2 than just adding $80 every single time. So it's not going to be that same linear kind of growth like we saw with our simple bond, but now where something else is happening in between here. So, and with our 8% compound interest, this seems like it might be something else. So what if we try to find what's our, maybe it's a geometric type of looking thing or exponential function, if we can find the multiplier between two of these terms and see if it matches up to see if we have a multiplication between these terms instead. So I'm going to try that with a couple different things here. So if we take any term divided by the previous, we can get our multiplier. So again, b is equal to, let's take 3 and 2. If we go 1,259.71 divided by the previous term, which is 1,166.40. If we plug that in our calculator, our multiplier is 1.08. Okay, so that's great. What about if we do it between 1 and 2? Let's check it. If they match, I think we got an exponential function. So if we have b is equal to any term, we'll do term 2, 166.40, all divided by 1,080.0. If we divide that, again, we get the exact same thing, 1.08. So this is this is being represented by an exponential function where our multiplier between every two terms is 1.08. Which hopefully that kind of makes sense to us. When we talked about our geometric sequences and we're talking about percent increases or percent decreases, we had those with like population problems or values of cars and things like that in our homework. When we had something that was increasing its value, we took that 100% of the original value, we added the percent that it's increasing every single year to that 100%. And that's kind of the same thing that's happening here. So if we're compounding our interest every single year, we're taking 8% of the previous year and then adding that on to the original value. So again, that's why we're going up by a different amount every single time. Because for example, when we're going from year 1 to year 2, we're taking 8% of year 1 and then adding that onto the total for year 2. So it's not just adding the same 8% of our starting value like we had for our simple compounding interest. So that's why it's growing by a multiplier of 1.08. So again, because we're taking 8% of the previous year, adding to the new total, or to get our new total, not just taking 8% of the original initial value. So what will the value be in our credit union account by the end of year 4? Again, all we're going to do is take our value for year 3 and multiply it by 1.08. And when we do that, we will get 1,360.49. Perfect. One last part we want to answer was 730, and that is part E on the bottom of the next page, or middle of the next page, I should say. So what type of account, a bond with simple interest or a credit union account with compound interest, is going to grow most quickly? I think it's definitely going to be the credit union. And again, it's because we're multiplying by a number to increase, and we're going up faster and faster and faster, whereas that simple interest with our bond was just adding the same amount every single time. So it's still increasing, but at a lot slower rate. So the credit union, because it's exponential, will be growing significantly faster with that compound interest. All right, so now we're going to go to the next one, 731. Let's check our notes and see. Moving on to 731. So assume the interest is added at the beginning of every single year. So make one graph that shows how each type of investment, the simple and the compound, starts with $1,000 and then grows over 8 years. All right, so this is what we're going to do. I'm going to kind of walk us through this one here again, because this is going to be something a little bit different that we might not have seen before. So again, if we're only adding our growth at the beginning of the year, that means in between those years, our Y value shouldn't be changing at all. So again, if we're only increasing our investment at the beginning, it's going to kind of stay flat. And then when we get to the end of the year, then we're going to jump up again, because that's when we're adding our interest. So I made the graphs on the next page for us, so it should look something similar to this. So if we fill out our tables, again, following our patterns, we have kind of a linear growth of the value of the bonds. We're adding $80 every time we go down a row in our table. That graph looks kind of like this. Again, we're starting with $1,000. The blue lines represent the linear equation here. So basically, again, we're starting with $1,000. We stay at $1,000. We get to the end of year 0. Then we get to year 1, and then we add $80. So we jump up to $1,080. Then again, we stay level. We don't add our interest until we get to the end of year 1. When we get to year 2, we have an open dock. We don't include that right here. We jump up. Now again, we get to our next level, 1,160. Then we kind of do the same thing over and over again, where we don't actually increase until we get to the start of the next year. And then we have the value of the credit union account, which is again the exact same thing, but except for not linear. Now we have that multiplier between our terms. So this one's going to go up a little bit faster, as we can see both in the table and the graph, where we kind of start the same, but because that we're multiplying by that multiplier, it's bigger than 1, we're exponentially increasing. So again, those green lines here are telling us the exact same thing, where we're going up by 8% of the previous year's total, and then that's getting added on every single time. So again, we're not increasing until we get to the end of the year. At the start of the year, then we jump up to the 8% of the new total. Then we stay flatline for the year. Then we get to the end of the year, boom, we jump up to the next year, and then we keep going from there. So again, that's what these functions should look like when we graph them. Again, because we're not continuously increasing that Y value of the bank account, we're only increasing or getting that interest added to it at the beginning of the year. So for the whole rest of the year, we need to keep that Y value the same in between those 2 years. So that's what we should look like. So if we turn the page, we're going to go answer a couple more questions about these 732. Questions are the graphs on the last problem, or something we can call step functions. Again, because if you go back, it looked kind of like a set of stairs, where it's flat, then we go up, flat, then we go up, flat, then we go up, and so on and so forth. So we call those step functions. That's because our Y value isn't increasing in between terms. It's not until we get to the very next year that we're adding the value into that bank account. So, all right. So thinking about those two functions from 731, think about the growth in the starting point for the simple and the compound interest situations from this model. And I want us to make two equations that represent each situation. So like we kind of talked about, one was looking pretty linear, the other was looking pretty exponential. So again, we have two equations. One is going to look like this: y equals mx plus b. M is our slope, b is our starting value. Our exponential functions are y equals a times b to the x. Again, a is our starting value, b is our multiplier. So what I want you to do, pause the video, go back, look at our tables, and write the two equations that represent both of those situations. So pause the video. Perfect. Hopefully you paused it and wrote down the two equations that represent those two models. For our bond, when we have our starting value, that's $1,000, we're adding $80 a month. That is our slope. So we can think about that equation as y equals 80 times x plus 1,000. And this was for the bond. Perfect. For our credit union account, that was our exponential looking one. Our starting value was still $1,000, so we should have A for 1,000. And then like we talked about before in the video, our multiplier was 1.08. And that is what our equation should look like for the credit union. So hopefully that is what we got. So we want to use our models next to predict how much our original investment is going to be worth at 20 years. How much our original investment is going to be worth at the end of 20 years within the credit union. So again, our credit union equation is right here. If we have 20 years, that means x has got to be equal to 20. So now we just plug it in and evaluate. So y is equal to 1,000 times 1.08 to the 20th. Remember, we got to evaluate this term first. order of operations, we have to do exponents before multiplication. So do 1.08 to the 20th in our calculators, multiply that by 1,000, and after 20 years, we will have $4,660.96 inside of our credit union savings account. Perfect. So last question for this one. Why are these equations considered models instead of a representation of the real behavior? So again, if we go back and look at the growth on these graphs, for example, if I just look at the blue one, the linear one, the one that looks like it should be a linear equation, if I kind of if I actually draw that line in here, where we're actually growing is only at the left-hand points of those lines. So again, it's a model because it represents the growth. But because we have this step function in between, we're not actually adding any money until the end of every year. We're only adding at these points right here. That graph or the line is really only accurate at those very few points. So we only consider it a model because it's not accurate 100% of the time. It only kind of gives us the rough shape of that line. So it's not continuous. It's not 100% accurate because it only gives us the rough estimate of what that's going to look like, because the step function tells us more precisely what that growth is going to look like. Perfect, moving on. Let's go to 733 and we'll wrap this video up. So last one for today, well, let's do 734 on your own. We'll talk about that more in just a minute here. A third option for investing money is a money market account, which offers 8% interest or compounded quarterly. That means 4 times a year. So this means that 8% is divided into 4 parts over the year. So that means that the bank pays 2% interest every 3 months. So let's write a new equation that tells us how our money is going to grow if we're compounding quarterly when X is in quarters. X is the number of quarters. Again, Y is the amount of money. We're starting with $1,000 again. So again, this one's also going to be exponential because we're compounding that interest. So we got to find our new multiplier. Our starting value is going to be exactly the same. So again, our multiplier, we know we're adding 2% every 3 months. So I think that B value, like we talked about back in chapter 5, we take that 1%, we're adding 2% to it. So this has got to be for B, 1.02% for our multiplier here for this one. So our new equation, Y equals 1,000 times 1.02 to the X. All right, then using that new equation, how much is our value going to be worth after 4 years? So not just plugging in 4 for X for this one, because right now this is telling us X is the number of quarters. So if we just plug in 4, we're only looking for 1 year right now, because we need 4 years. So there's 4 quarters in a year, 4 years, 4 times 4. We need X to be equal to 16. X to be equal to 16 in this case. So if we plug in 16 for this equation, Y equals 1,000 times 1.02 raised to the 16th power. If we evaluate that, we will get $1,372.79. So if we compare that to our other 2 equations, if we go back in our notes to our tables, after 4 years, which one is going to be the highest? Again, keep in mind $1,372. Let's go back and take a look. At 4 years here, we've got 1,320, 1,360.49. So if we compound more often, we're going to be making more money long term. So again, compounding more frequently, we'll be making more money faster, instead of just compounding once a year or just doing the simple interest with our bond. All right, folks, so that's where we are going to stop for today. Take a look at 34 on your own, kind of a challenge problem. If you can figure that one out, great. We'll have the answer for you in the filled in notes. Other than that, the homework for tonight is 7.1.3. Make sure you skip 739. We don't know how to do that one, so don't worry about it. Other than that, that's where we're going to end for today. Hope you guys have a great day. We'll see you in live class tomorrow.